All right, so friction. There are two basic models of friction. One model I call the Nook and Cranny model. The other one I call the attraction model. So if I have a book sliding across a desk, or let's make it a box sliding across a desk since that's what's sitting right here. So for those who need a visual, it's not picked up on film, so if you missed it, you probably will never know what I just did. So I have table, I have box. And if we zoom in on the surfaces, so the box, if you zoom in close enough on the box, it is not a level surface. But then again, neither is the table. Just emphasizing blue for the table and green for the box. Under this model, you basically, it's kind of like jigsaw puzzles. You got these pieces right here, not interlocking, but interfering with each other. And as you try to move it, you have difficulty here because there's somewhat of an entanglement here. So in order to move it, it either needs to come out of the grooves, or some of these things need to break off. Now the idea in this model is that once you get it moving, either you've broken some stuff off, or it's sliding over the tops. As it slides over the tops, it's a lot easier to move once you get it moving. So there's a difference between getting it to start moving and once it does move. Now, the nooks and crannies depends upon the surfaces. And the surfaces, so friction depends upon the surfaces, and that is bundled up in what is called the coefficient of friction. Coefficient of friction. Now in this model, they do differentiate between whether it has started moving or not. So if it hasn't moved, you'll use what's known as this coefficient of static friction. Coefficient of static friction. It's static, similar to static equilibrium, where static equilibrium means it's equilibrium where the object's not moving relative to the observer. Here, coefficient of static friction is the coefficient of friction when the objects are not moving relative to each other. And then there's this kinetic coefficient of kinetic friction. Sometimes I throw the descriptor in front, so the static coefficient of friction or kinetic coefficient of friction, so I think I could just go pop static or kinetic either up front or right before friction. So it differentiates between these two. The other thing that is going to depend upon is how tightly are these two items pressed together. So if I have it like this, that would be much less friction than if they are really shoved into each other. Well, what force is associated with how much two objects are shoved into each other?
Weight.
Not weight.
Normal force.
Normal. And so friction depends upon the surfaces and depends upon the normal force. Now the formula I'm about to write down was first developed in the late 1700s, and it's still the one that we use today. So the kinetic friction is the simplest one. So kinetic friction is equal to whatever the coefficient of kinetic friction is times the normal force. Static friction is a little bit different. All right, so right now, is the table accelerating from our point of view?
No.
All right, I'm going to push on it a little bit. Is the table accelerating now?
Yes.
No.
How much?
You're moving, you said.
Is it accelerating now?
No.
Okay. Oh, you're talking about when I first touched it?
Yeah.
Okay. All right. So so right now, is it accelerating?
No.
All right. Is it accelerating now?
No.
What about now? I'm pushing harder as I do this. Is it accelerating now?
I can tell.
So let's say that at that point right there, I'm applying 10 newtons of force on it that way. What is the friction force acting on the table? Yeah, they have to balance out because the acceleration is 0, so the total force is 0. If I apply 20 newtons now and it's still not accelerating, what's the friction force?
20.
So the static friction is going to match the applied force up until a certain breaking point. Once I reach that breaking point, it starts to move and kinetic takes over. So static friction is less than or equal to mu sy. So mu s times y, this part right here, is the maximum static. That's the breaking point. If I plotted applied force versus friction force, the friction is going to match the applied force up until I hit a breaking point. Once I hit the breaking point, it's going to drop down and the friction will be constant. So this point where it drops down to, this is my kinetic friction. This point right here at the top, this is my maximum static. So that's basically what the friction versus applied force will be for an object that starts out at rest and I get moving.
Is kinetic friction always less than the friction static max?
I've never seen a case, from an official table where it has not been. Sometimes they're really close to each other that you can get away with just rounding to the same thing.
But it's still typically just less than.
Yeah. Now, I've seen plenty of student experiments where they get mu sub k greater than mu sub s. Again, another Nobel Prize. Just waiting for the world to catch up. There's actually been surprisingly very few studies over in nitpicky detail. And I'll explain when I'm done about why I believe that's the case. All right. Any questions about this right now? Notice we do have some other independent equations for substitution, the substitution part. All right, under the attraction model, if you blow this up, what you have is two surfaces here, and they are attracted to each other. You have atoms down there, or molecules, depends on the level you want to go to, and they actually have an attraction towards one another. And that is what causes friction. It's nothing to do with the nooks and crannies, but just the fact that on an atomic level, they're attracted to each other, and the friction is just the resistance to get them apart. Under this model, there is no differentiation between the static and kinetic coefficients. The argument I've heard is that the experiments that are done to determine mu sub k and mu sub s have very large error bars. Yeah, you look it up and it'll go, the coefficient of kinetic friction for these two surfaces is 0.1, and for static is 0.2. But any experiment you do in science, there's a range. And what they don't state is it's 0.1 plus or minus 0.1 and 0.2 plus or minus 0.1, and there's a lot of overlap. So in this case, what you have is that the friction force is less than or equal to mu y. And if we plotted applied force versus the friction force, the friction will match it up to the breaking point, at which point it levels off. And so this point right here is mu y. So which is the model? I tried to find more detailed information because surely, there are very two clear, distinct differences here. surely somebody has actually done this experiment. I can't find it. I did find one person as a part of a senior college project, go through and actually do friction with error bars, and the error bars were so large, as these people claim, that it was really hard to come to any decisive answer. So I bring them both up because right now almost every physics textbook does this model right here, the Nook and Cranny model. Your textbook included. The 251, 252 textbook that we used before the one we currently have had a page on this model, but they used that model. So there's sort of a very long, slow transition. American textbooks also tend to be a lot slower in the change. So, it's possible your kids or grandkids might see the shift over to here, or it's possible that they won't. Now, the reason why there are two models, but people still stick with this one, is friction is generally something that physicists don't deal with. That's an engineering issue. Engineers have something that works. Engineers, as a generalization, are very practical people. They have something that works. Why bother tinkering with it? So, and again, engineers have something that works. Physicists don't deal with it enough, and so that's why this has been around for several hundred years. There is a group at NC State which is trying to come up with a better or more in-depth knowledge of friction, and I suspect they're not going to come up, at least from the talk that I saw a couple years ago, they're not going to come up with anything that is simpler than this. It'll be a much more sophisticated equation that is, from a practical point of view, not particularly. But I at least wanted to introduce this to you, even though we'll be doing that method over there. Any questions? Jennifer?
It's kind of a random question, but why is it when you apply a lot of friction, it creates heat? Like when you do this? I'm just curious.
All right, we'll get to it in chapter 7, when we deal with energy. But there's this idea of conservation of energy, that anytime that you apply a force over a certain distance, that you're transferring energy from one form to another or one object to another. So when you rub your hands back and forth, the energy in your hands, you basically have kinetic energy of your hands that, based on how fast they're moving, your hands are not speeding up as you do this or not really slowing down as you do this. Yeah, there's a cycle to it, but my hands are still, when they're in the same position as they were before, going just as fast. So, but I'm applying a force over a certain distance, so that energy is going somewhere. And so that energy is going in on basically making the atoms move faster, which we register as temperature. That's what's happening there. And there's an experiment where you take iron filings in a can or something like that, and you just turn it upside down take a temperature measurement, then turn the can upside down a certain number of times, so that all the particles are moving from one end to the can to the other, and then looking at how much the temperature changes from doing that. And so connecting temperature to movement. Is that sufficient?
Yeah.
Other questions? All right. So enough of this newfangled stuff. All right, so for a box on ramp problem, assume the initial speed is not 0, and the direction of the initial velocity is down the ramp. In other words, let's not worry about the static piece right now. Let's assume that it's already moving down the ramp, and I want to know what the acceleration is. We do need, since we're introducing friction now, mu sub k, we will make 0.3. And let's make mu sub s equal to 0.8. But since it's already moving, I really don't care what mu sub s is right now. That'll come in the next variation of this. All right, so questions about what the problem is? Still finding acceleration.
I'm sorry, can you rewrite what's written in red?
Oh,
I can't see.
sorry. Assume, can you see that well enough?
Yeah.
The initial speed is not 0. In other words, it's moving. And the direction of the initial velocity is down the ramp. Probably could have written that in fewer keystrokes, but that's weird what I did. So it's moving down the ramp when the problem starts. For those who need a visual, we start the problem now. Any other questions right now? All right. Force diagram. What changes in our force diagram?
Friction.
Which way is friction acting on the box? The friction is acting this way and down on the ramp. So we still break weight up into the force diagram. Acceleration is still the same. Coordinate axis is still the same. Decomposition is still the same. And so all the thing that's changed is we've added this friction to the box up the ramp. And that gets us down to through decomposition. We don't have to break friction up because it's in the negative I hat direction, so nothing to break up. Equations of motion. How many equations will there be?
2.
2. Is that what you're going for?
Yeah.
Okay. What are they? Again, go and redraw the axes down closer to the diagram we're using right now. Where are really dark markers? Considering they're not on the floor anymore. Let's see if any of these work. Not particularly. That's the J hat direction, and that's the I hat direction. All right. What are the two equations of motion?
Y minus W cosine theta equals M0.
And we'll just jump straight to equals 0. And the other equation?
S of K minus W sine.
W sine less.
Down is positive, down the ramp. So W sine theta minus F sub K, all right.
Equals M times A.
And now, substitution. For what do we have an independent formula? I heard weight and,
Friction.
yep. So I have Y minus M. I'm just going to go ahead and jump to the next step. Y equals mg cosine theta. And for this one, we have mg sine theta minus mu ky equals ma. Now it's a math problem.
Is that N or F? NKY?
But here,
Yeah, one more. No, I mean, is that an N?
It's mu.
that's a
Yeah.
mu.
Uh,
The coefficient symbol. It's like I didn't really put the right side stem. It's like the letter U with a handle on the left side. Like opera glasses. at least one mu neatly. It's like the letter U, and then you have the stem up front. That's a mu. All right. Questions, other questions? All right, so to solve it, I know what the mass is. I know what mu sub k is. I know theta, I know g, I know the mass. I know everything except for y and a. And a is what I'm trying to find. But I have a formula for this problem for y. It's not always this formula. It is specific to this problem. So what I'm going to do is I'm going to take this problem-specific formula for the normal force and just plug it into y. Since y is equal to it, I can interchange them. So I'm left with mg sine theta minus mu k times mg cosine theta is equal to mass times acceleration. So what I've just put in parentheses right there used to be the letter y, used to be the normal force. I now have three terms. Term being that which is separated by plus, minus, or equal signs. That is an equal sign there, despite the way it might have looked. Is there any factor that is common to all three terms?
Mass.
So ultimately, the mass does not matter. And so I now actually have a formula for acceleration. The acceleration of this will be g sine theta, that's what we got when it was frictionless, minus mu k g cosine theta.
Why can't you cancel out all of the masses? I thought that you can only cancel out one of them.
Technically what I'm doing is, on the left-hand side, I've got two terms here. And the term, I have three things multiplied together for that term and four things multiplied together for this term. I'm factoring mass out officially. So this becomes mass times g sine theta minus mu k g cosine theta is equal to mass times acceleration.
Okay.
And then I divide by the mass. So that cancels out, that mass cancels out.
Okay.
That's the long way.
All right, thank you.
Mm-hmm. So this is 9.8 times the sine of 57 degrees, which I think is 8.22, if I recall correctly, minus 0.3 times 9.8 times the cosine of 57 degrees. About 1.5?
1.6.
1.6? Give me one more decimal.
Oh,
Okay, 6.0. And so 6.62.
Meters per second squared.
And as expected, with friction, it doesn't accelerate as quickly. If I made the angle steeper, this term would get bigger, and this term would get smaller, because the steeper the angle is, closer it gets to 90 degrees, the smaller the cosine of the angle gets. And the larger the sine of the angle gets as I get steeper and steeper. So it'll accelerate faster, not only because it's closer to just a straight drop, but it should get faster because my friction is getting smaller. Because the box and the ramp are not pushed against each other as much as I get steeper. Questions to hear? All right, so I'm gonna basically take the same problem, except I'm gonna make one change to it. assume,
Oh, great.
okay, let's not go for here. The initial velocity is 0 meters per second. I've now changed the problem so that the object starts at rest. In a problem like that, the first thing you need to do is you need to figure out, is it actually going to start sliding? So you do the problem as if this is f sub s. And I know it's a lot easier on me on the board just to change one letter than it is for people who are writing the notes from scratch again. But a little bit of pause here. So people catch up.
So when you just calculate acceleration,
You trailed off. I assume you sort of resolved your own question.
it's a lot more complicated than that.
All right, so Keelan, first of all,
Would it change anything about the calculation?
it will because those are different. All right, Daniel, what was your question?
No, it's a lot more complicated. I just kind of did in my head.
Okay. Now, notice that what I'm doing is all I've done is that I put in mu sub s. I am pretending that the static friction is equal to mu s y. Now, it's not necessarily the case. If it's not moving, that's not necessarily the actual static friction, but that is the maximum. What I'm trying to figure out is, am I exceeding the maximum amount? There are ways of doing it. I'm trying to take it, again, through the process. So, and again, the advantage of not putting any numbers in until the very end is all I have to do now is just change that. I change the letter S, and I actually have only that calculation to do in a subtraction problem. I don't have to start from scratch again. And so what is the maximum static friction here? Or at least this piece of it.
4.27.
Say it again.
4.27.
And we end up with 3.93, I believe. So what is the conclusion? Is it going to slide?
Yes,
Why? What's your...
because it's still acceleration is still positive.
Therefore, what is the acceleration of the box down the ramp?
Meters.
Wait, what'd you say? That was look, I actually did not, it sounded like you said 0.92, but it wasn't.
So 3.93.
And that is not the acceleration of the box. I was hoping somebody would say that, just so I could say, no, that's not it. So thanks for playing along. Why is it not 3.93 meters per second squared?
Isn't that just the breaking?
Oh, it's the indication that we're past the breaking point. This is if we are at the maximum static, but once we establish that it's sliding, then we go back and put the K's in. The actual acceleration is whatever we got the last one, was 6.62 meters per second squared. That's the actual acceleration right there. Now, the next lab that you do, the one, I guess in 2 Tuesdays, part of the pre-lab is I'm taking, this is very much like the pre-lab problem. All right, I'm gonna change the problem slightly one more time. Oh, add in here. Therefore, box slides. Therefore, the coefficient of friction should be the coefficient of kinetic friction. And that's what we got the last time we did it. And now with the magic of the fact that most of it's written on the board already, I'm gonna up some frictions here. I'm gonna up the static coefficient to something that's absolutely ridiculous. Use of S is 2.8. I've never actually seen any official coefficient of friction bigger than 1. So I don't know if there's any theoretical reason why it couldn't be, but I haven't seen it. I think once you get perhaps above that, like Velcro might have the illusion of friction, but it's not really friction that keeps Velcro, it keeps things sliding with Velcro. I think it's more hooks and loops. What is this now?
14.94.
14.94? And so this becomes negative 6.72. Therefore, what is the acceleration of the box?
0 meters per second squared.
Because this answer is impossible. Because the meaning of this is the acceleration is negative, which means I put the box on the ramp and suddenly it accelerates up the ramp. That would be really cool if we could pull that one off. And probably lead to the destruction of all mankind. But besides that part, again, just like the mushroom cloud from a nuclear bomb, it is really cool as long as you don't think about what's actually, the destruction piece of it. The box is, we cannot put a box on a ramp and suddenly have it move up the ramp. So this means this is an impossible answer, therefore not sliding, therefore not moving in our case, therefore the acceleration is 0. And when I say not moving, I'm not talking about the speed is 0 for an instant, like I throw an object in the air. This is not moving as in, it is not moving for this sustained amount of time.